Let's have now a tutorial on second-order circuits both in the time domain and using the Laplace transform technique. Our first exercise comes from the textbook by Professors Alexander and Sadiku, exercise 837 asterisk. The asterisk identifies this problem as a challenging one. The circuit is right here on the figure, and the problem says that switch has been closed for a very long time, which is to tell the student that the circuit is in steady state. Because the two sources are DC, the circuit is in DC steady state. Now, first, we find the initial conditions in the inductor and the capacitors. We will need them both. And for that, we will take a snapshot right before the switch opens at t equals 0 minus. There is your snapshot. And you may be thinking, wait a second, where did you take that equivalent circuit from? Please show me the original circuit. Here it is. Check it out. It's in DC steady state, right? So that means that this inductor behaves as a conductor, as a wire, this conductor. And the capacitor is fully charged, so it behaves as an open circuit, this open circuit. The only part of the circuit that remains is this one here, as shown. And in there we need to compute this current, IL0, which is the initial current in the inductor, and also this voltage, VC0, the initial voltage in the capacitor. How do I do that? Well, observe that this circuit has basically, once you simplify this 6 ohm resistor and these two series resistors 6 and 6 into a single resistor of 4 ohms up here, it's a single loop, and that current is the value of the two sources divided by 4 ohms. Let's write that. That is 4 ohms, right? So that current is 45 minus 15 divided by 6 in parallel with 6 in series with 6, which is 4 ohms as shown up here. That is 30/4, 7.5 amps. That is the initial value of the current in the inductor. That is IL0. What about VC0? Well, if only we knew the voltage in this 6 ohm resistor, VC0 would be 15 plus that voltage. But that voltage would be easy to find if we also knew this current Ix. That voltage would be 6 times Ix. But you say, wait a second, if I choose this node as my reference, this one here is at 45 volts above the reference, and this is at 15 volts above the reference, so that current on the top branch would be 45 minus 15 divided by 12 ohms, and that is 2.5 amps. 2.5 amps times 6 ohms would be 15 volts up here in the resistor. So that means that VC0 is 15 plus 15, 30 volts. We have the two initial conditions for this circuit. Let's move on. And now we go into the Laplace domain, and this is the topology of the Laplace domain circuit. You say, wait a second, what is with all of those gadgets in there? I'm counting more elements than there were before in the original circuit. Let me show the original circuit. There's one. This one. You say, after t equals 0, this switch is open, so this branch on the left lower side of the circuit is gone. And you say, I buy that. The 3 resistors remain being 6 ohm resistors. That hasn't changed. This source down here, 15 volts in the Laplace domain, becomes a 15/S. What about these two and those two? Well, the inductor in the Laplace domain is represented by two components, an impedance SL and an initial condition source L times IL0. And the capacitor similarly is represented by an impedance 1/CS in series with an initial condition source VC0 divided by S. This is LS, 1/2 times S, and for the capacitor 1/CS, that is 8/S. This initial condition source would be 7.5 times L, and that is 1/2, which with integer numbers is 15 over 4. That is that value. And this one is the initial voltage in the capacitor of 30 volts divided by S. We are ready. That is the Laplace transformed circuit of our original one for t after 0. And in there, those three resistors are simplified to a 4 ohm resistor. And we're left with a single series RLC circuit with three sources. Of course, the current we want to find is IL, the current in the inductor, as a function of S, the Laplace transform of the current in the inductor, and that in that one loop circuit is merely add the sources divided by the impedance, like so. I type that in the calculator and use the simplification button F6 thanks to Mr. MacBeal, and that is the Laplace transform of the current in the inductor, this one, and exponential in the time domain. Inverse Laplace, and that is our current. 15 over 2 exponential of negative 4t. An exponential with a time constant of 1/4 of a second, and that is the solution to that challenging exercise according to your textbook. Let's solve now the same circuit, but not with the Laplace technique. Let's use that. Let's solve that instead in the time domain. And for that, I will be using the Heaviside operator, the P operator that I described in detail in the previous movie. We will need, of course, another snapshot. This time, a snapshot of the circuit at T0 plus, right after the switch opens. We know that the current in the inductor and the voltage in the capacitor for that particular instant will not change. It will remain being whatever IL0 is and VC0 is. So for all practical purposes, in that infinitesimal slice of time, at T0 plus, the inductor behaves as a current source with its value IL0 and the capacitor as a voltage source with the value VC0. This way, right? That is our representation of the circuit for an instant right after I open the switch at T equal 0 plus. And in that circuit, once we simplify the three resistors again to a 4 ohm resistor, we have a very easy time. The current in that loop is IL0, right? That current is known. And what we need to compute is the voltage in the inductor at 0 plus VL0. For that, I will write a KVL equation in that loop. Let's see, around here. I'm going to travel that loop clockwise just because I could travel that counterclockwise if you prefer. Going up by 15, going up by VL0 unknown, and going up by 4 times IL0 and going down by VC0, that has to be equal to 0 according to Kirchhoff or Kirchhoff. From there, the only unknown is VL0, and we solve for that and replace for numerical values and get that VL0 is negative 15 volts. But I don't care for VL0. I care for the derivative of IL0 with respect to time at 0 plus. I divide that value by the inductance 1/2 of a Henry and get that DIL dt at 0 plus is negative 30 amps per second. Now we have the necessary initial conditions, right? In the time domain, after t equals 0, I use Heaviside to find the differential equation that I need to solve. I take the circuit at t after 0. I replace all the reactive elements with the Heaviside impedances LP for the inductor and 1 over CP for the capacitor. Nothing happens to the source. We are still in the time domain, 15 volts. And we solve there for IL, and what we get in reality is a differential equation. It is a second order differential equation. The coefficients are 1, 8, and 16. The solution is IL of t, and on the right hand side we have 0. That is our differential equation. Well, that differential equation has only one eigenvalue. That means that circuit is critically damped. The form of the solution for that one eigenvalue b equal 4 has this shape. A ramp k1t plus k2 that multiplies the exponential of negative 4t. What about k3? What of the steady state of that current? You say, well, in that RLC series circuit, the final value of the current is bound to be 0. We have a DC source. In the end, the capacitor will be fully charged and the current will not flow anymore. So that is our current. But we have the initial condition of IL, 7.5. We have the initial value of its derivative, negative 30 amps per second. So we can find K1 and K2. 0 and 7.5. Substitute them here, and you find that the current in the inductor as a function of time, it is 7.5 times e to the negative 40 amps, which is exactly the same we obtained using the Laplace technique, but with a little bit more effort this time. Now we turn our attention to a circuit that has what you all were waiting for. It has op-amps, 2 of them, 2 resistors of the same value, R and R, 2 capacitors of the same value, and 2 ideal op-amps. Because there are no power supplies indicated here, the implication is that none of the op-amps is saturated. You know that. But if they are not saturated, the only way an op-amp is not saturated, we remember from our previous course, is that there is negative feedback. But if there is negative feedback in an op-amp, Vp is equal to Vn. And Vp is 0 in both of them. So that means that this voltage here, Vn, is 0. And this voltage here, all the way here, is 0 too. Oh, that's nice. Let's put some labels there. This current is the input to an ideal op-amp. It's null. So is this current here to the non-inverting input of the op-amp on the right-hand side of the circuit. Output voltage V0 and output voltage of the leftmost amplifier V01. We'll remember our warning about not writing case-scale equations for the output nodes of op-amps unless we know the voltage at that node. If we know V1, if we know V0, sure, you can write a case-scale equation here or here. But right now we don't, so we do not write a case-scale equation for the output node of either of those 2 op-amps. We write a case-scale equation here though, and another one here. And immediately you jump up and say, hey, wait a minute. We were told, learning M&A, that we never write a case-scale equation for the reference node, for the 0 volts node, for the ground node. Well, that is true, you see, but this node is not the reference. This is not ground. It only has the same voltage as ground as your reference. The reference is down here. This is only a virtual reference, a virtual ground. So we can indeed write a case-scale equation here and there, and we do. For this one on the left, only one current arriving, this one on the top, V0 minus 0 divided by R. There is the reactive elements in the Laplace domain. This capacitor has an impedance 1 over Cs and an initial value of 2 volts, which is given. The other one is discharged at first, so that's why you don't see any IC source in this part. We're ready. Writing the first case-scale equation for this one. Current going in, V0 minus 0 divided by R, this one, and that is equal to the one only current leaving the node, this one through the capacitive branch. 0 minus V1 minus 2 over S divided by the impedance, that is this term. Another case-scale equation for this node, the non-inverting node of the rightmost op-amp. Currents going in, V1 minus 0 divided by R, V1 over R, and that is equal to the only one current leaving the node, 0 minus V0 divided by the impedance. two equations, two unknowns, and we solve for V naught, and this is what we get. The Laplace transform of the output voltage of that combination of op-amps, resistors, and capacitors. To find the differential equation, because the exercise says find the differential equation whose solution is V naught. Well, to do that, all we do is we zero the initial conditions in the circuit, and then what happens if this is 0, this 2 is 0, if this 2 would be 0, this 2 is 0, and we are left with this differential equation. It's a second order differential equation in V naught with a second order coefficient r squared c squared and a zero order coefficients of -1. So it is a second order system, all right? But now that differential equation, we better write it like this to present it to the marker. When we find the inverse Laplace transform of this expression at the top, we get the sum of two exponentials. But check it out. While the second term, the subtracting term, will die off 5 over RC seconds later, the first term keeps growing without bounds. This circuit is unstable. I have replaced R and C's values into this expression to get the final answer to the problem. That is V naught as a function of time for this unstable circuit. And now an easy one, or maybe not that easy. You see, the configuration is misleadingly simple. Series RLC, but the source is the sinusoid, is 3 times the cosine of 2t. Let me take that circuit over to the Laplace domain. Yeah, 2s, 1 over 5s, and the source would be 3 times s divided by squared plus 2 squared, and the resistor will be 3 ohms. It hasn't changed. Well, the current is this one. What we need to find in the Laplace domain is the source divided by the impedance. Nothing really to write home about. We simplify that, and then things become interesting. You see, because this Laplace transform will drive the HP50G nuts. It will not be able to figure out left from right or top from bottom in that transform. It will give you back gibberish and garbage, absolutely useless stuff. How do we deal with that? The HP50G anyway. What I'm going to do, and this has worked for very complicated Laplace transforms on the HP50G in my experience, is I break that Laplace transform into a partial fractions expansion with the calculator itself, and then I ask the calculator, now find me the inverse Laplace transform, and not a single time has it failed to give me the right value, at least in my experience. Let's see what we have. Let's type that Laplace transform in the calculator using x instead of s, because that is the independent variable up here. So I go and ask for the partial fractions function, which is this one. You see, the first is an exponential term, another exponential term, and here we have something like looks, I don't know, perhaps cosine, sine. So gotta figure that out, because I cannot read all the way there. And so what I'm going to do is I will go to the white shift, PRG, type, and in this menu I use this key, this function here, break the object on the level 1 of the stack into its fundamental parts. I click on that, and it says linked by the plus sign. There are 2 parts on level 4 and 3. Those were the parts. You say, oh yeah, I delete the extra. Yeah, I swap them, and then I apply that to this one. You say, hey, that expression, break that object into its basic parts, and again it says, well, it's a plus that links them, etc. Now I have the 3 parts, the 3 partial fractions in that expansion. The that will become exponentials, this one and the level in level and the one in level 2, and this one, which is the sum of a cosine and the sine. This term is pretty much null. You say, why does it write 0.000x? Possibly because that 0.000 is 0.0000001 somewhere, and the calculator says it's not really quite zero, but it is to us electrical engineers from a practical point of view when the other terms are 4 and 1. So now that we are there is when I will ask for the inverse Laplace of each one of those partial fractions one by one, the first one, and then I go with the up arrow key twice. You see this cursor up here. I move it all the way to the level 3, and then I click on this function, which is roll down. Roll down. It will take those 3 entities in the first 3 levels, the ones I have selected. I could have selected 4 or 7 or whatever, and we'll roll them down. Roll down. Now the one that was in level 2 is in level 1. In level 3 is now level 2, and the level 1 is now on level 3. It rolled them around, rolled them down. Well, I do the same. Find me the inverse Laplace transform of these. There. You say that's fine. You have the 2 exponential. Swap. Find me the inverse Laplace transform of this. Click. You say, okay, as I had guessed, a cosine minus a sine. But still, I don't quite see what's going on there. Okay, so break the object into pieces, right? Break that object into pieces, and I say the last sequence is a combination of 2 terms in 4 and 3, 2 terms. Subtraction. You say, okay, instead of subtracting 0.4 something, I would just change its sign. You see, negative of all of that. Those are the 4 terms of our function of time. 2 exponentials, a cosine, and a sine will be negative 0.373 e to the negative 1.43 t here, the first term, right? Plus the next one. You say the next one is this one, 0.001 exponential of negative 0.070x, which is time, right? Is this one. You say, hey, you copied more non-zero digits there. Well, that's really nonsensical of me, because you see, I will be adding this exponential to this one that has a much larger amplitude, and the cosines and the sines. So this will pretty much will be shadowed by the others. But anyway, I run it down. How? Well, I went to this expression here, this one. I rolled it down in a way that I got it up. Actually, I rolled up, brought it back to level 1, and then down arrow took that expression to the equation writer, where I can see the full detail of each one of those coefficients, this one and that one as well, if I need it, just so you know. And that is the solution to this exercise. There are a few points to think about when we use the HP50G. You see, sometimes when we try to find the inverse Laplace transform on the HP50G, we get an exponential expression with complex coefficients like this one. Complex conjugate coefficients, 2 exponentials, and the exponents are also complex conjugate. You probably have seen this before and deleted it right away. You didn't want to deal with that. The reality is that that is a correct answer, and that answer can be simplified and consolidated into this one. That expression is a decaying sinusoidal oscillation with a frequency 20 radians per second, a decaying rate of -5, that is, the time constant is 1/5 of a second, 0.2 seconds, and it has some amplitude. I'll show you that this amplitude in reality is 2 times the absolute value of this complex number here, and the phase shift, which I'll show you, is just the argument of this complex number as well, the angle of that complex number. Let's go to the next page. and be patient. We're going to do some major arithmetic here. We begin with that expression. I've simplified them using letters AB, A negative B, they're complex conjugate, and the exponents are conjugate as well. XY, X negative Y. I distribute the multiplication over the sum in each one of those complex numbers, A plus JB and A negative JB. Check it out. A times the exponential plus JB times the exponential. And I did something similar to the second term. And next, I go ahead and expand this exponential into two exponentials multiplication. E to the x multiplied by e to the j or y. And I do that for each one of the four terms. Fine. And now what I'm going to do is, first I factor out e to the x. You see it's in every term. And then I use Euler's identity to expand each one of the four terms, e to the imaginary number yj or negative yj. There is your expansion. In that expansion, let's review only one of the terms, the first one. This would be a times cosine y plus a times j sine y. Here it is, y a sine y. And the same for the other four terms. When we do that, in the end, we notice that this term is the same as this one. Oh, 2 times a cosine y. That is nice. What about these two? They cancel out. What about those two? They cancel out. What about this? Well, what is this? This is negative b sine y. What about this term? Minus times minus, that is plus, j times j, that is negative. This is also negative b sine y. So we have this expression, 2 times a cosine y minus 2 times b sine y. We factor out 2, and this is the expression. We can simplify that sum of exponentials with complex coefficients and complex exponentials into this one. We could leave it there, but I want to go in a little bit further, right? Let's take this expression, yeah, and consolidate that into a single cosinusoid like this. That sum of those two cosine and sine of different amplitudes is actually a single cosine of the same frequency, some phase shift phi, and a certain amplitude k. How am I going to find who is k and who is phi? Well, let me expand this cosine of a sum. You remember that? That was cosine of phi, cosine of y, minus sine of phi, sine of y. But if you compare this left-hand side of the equation on the top and this expansion of the right-hand side, you say there is only way that could happen. A has to be equal to k cosine phi, and B has to be k sine phi. Two equations and two unknowns, k and phi. Well, sure, non-linear equations, right? But two equations anyway. If we square both equations and add them together, we're going to get this one on the top. You say, how come? Sure, you're going to get k squared sine squared plus k squared cosine squared. That is k squared. Remember, sine squared plus cosine squared was 1, right? And it is on the other side. And if you divide them, k cancels k, and you get b over a is the tangent of 5. That's how we find them. So we go back to this expression and say, in reality, the original expression, this one, was 2 times this exponential that multiplies this k times cosine of y and the arctangent b over a. You say, holy cow, how am I going to remember all of that formula? It's easy. You see this term here, you can calculate directly from this coefficient AB. You just take the absolute value and double that, and this is the original amplitude of your consolidated oscillation. What about this angle? That is just the argument of that complex number. Easy to remember. But if we do that with numbers, we will remember it better, right? Let's do that with numbers. I copy the formula as a reference, and we have this combination. 3, 4, 3, negative 4, negative 520 times t. This time I included time explicitly. Fine. Well, that is bound to be 2 times 3 squared plus 4 squared. And the exponential with the decay will be e to the negative 5t. Oh, there is a negative sign missing here. E to the negative 5t, please fix it. Times the cosine of 20 times t. Yeah. And the arctangent of 4 over 3. We find these values, the amplitude and the phase shift, directly like this. And we say that actually is a decaying oscillation with an initial amplitude of 10, a decaying coefficient with a time constant 1/5 of a second, oscillating frequency of 20 radians per second, and a phase shift of 53.1 degrees. Neat, eh? And that is the end. That is all I have for you in these tutorials. If you have the patience to watch it to the very end, I really wish you the very, very best of lucks in your coming exam. Thank you very much, and I hope to see you again in the next movie.